Okay, let's start the seminar for the colloquium today. So thank you, Benjamin Jungfleisch, for joining us for the seminar for the colloquium today. So Benjamin Jungfleisch is an assistant professor of physics at the University of Delaware. His research interest ranges from various kind of magnetism-related effects, especially on spin transport phenomena and spin dynamic phenomena in nanostructures. He has received several research awards, and including early career research award and National Science Foundation fellowship. Before joining the University of Delaware, he was a postdoctoral researcher at Argonne National Laboratories in the Material Science Division, and he has his PhD from University of Kaiserslautern, Germany, in 2013. So let's welcome Professor Dr. Benjamin Jungfleisch, and looking forward to your talk.
Thank you very much for the nice introduction, and well, thank you for the opportunity. It's very exciting to give this presentation. So I feel really honored to present some of our recent results here. As I already mentioned, feel free to interrupt me if you have any questions. I'm going to talk about some recent findings in my group on basically nanomagnonics and artificial spin ice. So the title of my talk is Tickling Nanoscale Magnets, Nanomagnonics with Artificial Spin Ice. And for now, artificial spin ice, I will introduce the term. For now, let's just say that these are these array of nanomagnets that we pattern using electron beam lithography, and we are interested in the dynamics in those structures. So before I get started, let me just advance here the slide if I can. I want to mention the team and the actual people doing the work in the lab. That's first our graduate student Taba Tashipur Kafash. And he was responsible for most of the fabrication of the devices that I'm going to show. And our former postdoc Sergio Landines, who is now at LSU at Louisiana State University. We also have external collaborators, and specifically with Wanbei Bang, John Catterson, Federico Monticello, and Axel Hoffman. And I also want to acknowledge here funding support by the US Department of Energy. Why are we interested in these kind of studies? It was actually Gordon Moore who made an observation in the 60s of the last century, and he saw, or he observed, that the number of transistors per chip doubles approximately every 2 years. And this is now known as Moore's law, but actually it was more like an observation. Moore went on and was a co-founder of the Intel Corporation we are all very familiar with. And this observation became something like the driving force of the semiconductor industry. So they made it essentially happen that these numbers of transistors went up and went up and went up. But now, well, after 60, 70 years, Moore's law is approaching its physical limits. And we can see this here. Indeed, the number of transistors increased over the years. But at some point, something happened about 15 years ago. The speed was limited. So the clock speed was capped. Why is that? Well, as you make the devices smaller and smaller and smaller, heat and power consumption becomes a bottleneck, becomes an issue. And as a matter of fact, you can use the waste heat of your processor and your computer to fry or to bake an egg. All right. The other thing is, if you make things smaller, eventually you reach the end of scaling and quantum effects become relevant. And this means that your transistors will not work reliably anymore. You can either embrace this and do something like quantum computing, or you can think of alternatives or beyond post-Moore concepts. And I want to go this route. So this is the motivation for my talk. I want to rather use the magnetization instead of the electron's charge. And what I'm proposing here is to use waves or wave packets instead of particles. So usually in semiconductors, we use the electron. So This brings me to a slide about information carriers. In electronics, no surprise, we use the electron's charge degree of freedom, and that's just the flow of electrons. So this is the sum of spin up and spin down electrons. In spintronics, we use the additional spin degree of freedom. And in a conventional picture, we can regard a spin current as two electron currents with anti-parallel spin alignments propagating in opposite directions. And as a result, we can transfer angular momentum. And this is called a pure spin current. But nonetheless, you have still a movement of electrons. So what can we do about that? Well, we could think of using waves in the magnetically ordered material, and we call these waves spin waves, or if you prefer the picture of the second quantization, this is a magnon. So a magnon is the quantization of a spin wave, and this is illustrated here. Now, the beauty is we can transfer spin angular momentum by a flow of magnons, by a flow of spin waves, and we are entirely decoupled from the movement of charge carriers, so we can use magnons potentially in insulators. And this could reduce waste heat. All right, so here is an outline of my talk. I'm going to start with a brief introduction into spin dynamics and magnonics, the field that uses spin waves for potential information transfer and processing. Then I'm going to show you an artificial spin ice system and explain what it is, and the way I view it as a magnonic crystal. And for now, I mentioned it already, we'll just consider this term as an array of nanomagnets. Then I'm going to show you some results we obtained in my group at Delaware. I'm going to show you a comparative measurement between ferromagnetic resonance, that's a typical technique that we use in magnonics or in magnetization research, versus prolonged light scattering, which is an optical technique. Then I'm going to introduce a new type of magnonic crystal, which is based on a spin ice made of nanodiscs. And then I'm going to show you some exciting results where we observed some emergent spin dynamics facilitated by a bicomponent array of nanomagnets. And I'm going to close my talk with a short conclusion and outlook. So what is spin dynamics? And I have here this very intuitive video. So let's say we have a single magnetic moment, and this is shown here by this red arrow. Let's say this is a spin. Now we apply an external magnetic field. If there is a deviation from the equilibrium position, then there is a torque acting on the spin, on the magnetization, as you can see here. And as a result, the magnetization, the moment starts to precess. Now, in a real material, we do not have only one single moment, right? We have a whole ensemble of spins. And if they're all precess in phase, what you see here, this is called ferromagnetic resonance. Now you can have neighboring spins, you can allow them to have a phase difference. And what forms as a consequence of that is a wave. And that's the spin wave that I was referring to earlier. And again, the quasi-particles here are magnons, and we can define a wavelength, a wave vector, and we can do wave-based physics and phenomena and explore them in magnetically ordered materials. This precessional motion is governed by the Landau-Lifshitz-Gilbert equation, so that is the fundamental equation of motion of the magnetization here shown in red, under the influence of an effective magnetic field. So this is shown here in blue, and that contains the external field, microwave magnetic fields, anisotropy fields, dipolar fields, whatever you have, okay? And this first term here, this first torque is M cross H effective. This is the driving torque term illustrated by this green arrow. And as a result of that, the magnetization starts to precess. Gamma is the gyromagnetic ratio. Now, in a real material system, we have to face and account for damping, which if we do not have damping, then this precession would go for infinite amounts of time. That's not physical. So it was Gilbert who introduced this phenomenological Gilbert talk term, with alpha the Gilbert damping parameter. It's a dimensionless quantity. It depends on the material. And ms is the saturation magnetization. And the term here is m cross dm dt, and this is represented by this orange arrow here. And as a result of this talk term, the magnetization is pushed back towards the equilibrium. As a result, the magnetization spirals around the axis defined by the effective magnetic field, and in equilibrium, it will point in the same direction. So we can use this equation to model our results. We can do this numerically, and I will show you this later on. Now, why do I think are spin waves or magnons interesting as a post or beyond CMOS? CMOS is complementary metal oxide semiconductors device. And I want to list here some Magnon properties. First, I'm going to start with advantages. And the first is we can tune the wavelength down to the nanometer scale. We can have frequencies typically between gigahertz frequencies, but we can go all the way up to terahertz frequency. And we it's a different topic we are working on in my group, using terahertz spintronics, but it's not something that I'm going to talk about today. I just want to mention that you can push up the frequency limits here. You can use wave interference phenomena. Nonlinear dynamics are easily accessible, so that's important if you think about concepts like neuromorphic computing. You can have a reduced Joule heating if you use insulator. Remember what I told you earlier, that you can get rid of the motion of charge carriers. You can go to wave-based computing, which means you have a reduced footprint, and it's CMOS compatible. Disadvantages are that magnons are rather slow at 10 kilometers per second. And there are engineers, and I took this here from this paper, there are considerations and estimations that tell us that because you can go to wave-based computing concepts, you can make the area of your device 3.5 times smaller, that power consumption can be about 100 times lower. Because of the low velocity, the delay time is 10 to 20 times slower. That's a disadvantage. But nonetheless, this figure of merit, this area delay power efficiency, tells us these devices that are based on CMOS with some additional functionality enabled by spin waves can be 50 to 100 times better. So that's the technological background that I want to give you here. So magnons, for those of you who are not familiar with spin waves, I want to talk a little bit how we can create them, how we can detect them, what material platforms we can use. Since magnons usually have their resonance frequencies in the gigahertz regime, we use typically microwave excitation. That's the straightforward, the common way to excite magnons. We can use parametric excitation. You can thermally excite magnons. I have not considered this in the Landau-Lifshitz Gilbert equation, but you can add torque terms, so spin transfer torques, which also enable spin torque oscillators, or you can use ultra fast laser pulses. Today, I'm going to use only microwave excitation and thermal excitation. And on the other hand, detection-wise, we again can use microwave techniques. We can also use optical techniques such as prolonged light scattering spectroscopy or magneto-optical Kerr effect, so MOC. We can also use spin orbit effects or heating. Today in my presentation, I'm going to use microwave detection and prolonged light scattering spectroscopy. I already mentioned the properties. Let me summarize here the key properties. We can have a short wavelength, which is important for miniaturization. We can cover a large frequency range between gigahertz and terahertz frequencies. We have an intrinsic velocity and an anisotropic dispersion. Material-wise, well, we want to transfer spin angular momentum encoded in magnons. So this means we are interested in have a long decay length. And this means we are interested in materials with a low Gilbert damping parameter. So typically, the benchmark material is yttrium iron garnet YIG. That's an insulator. YIG is beautiful. You can do wonderful experiments with it. The disadvantage is it's pretty hard to not even to say to nanofabricate yttrium ion gun. It's pretty challenging. It's doable, but challenging. Much more straightforward is to use metals. And metallic materials with a low Gilbert damping parameter are nickel iron, we call this permalloy, cobalt iron boron, cobalt iron alloys, some certain cobalt iron alloys, and Heusler alloys. Today I'm going to use nickel iron, so permalloy, and cobalt iron. So I already mentioned we are interested in using magnons, the elementary quanta of spin waves, for information transfer and processing. And one example to this end are magnonic crystals. Magnonic crystals are magnetic metamaterials. These are artificial magnetic materials where we modulate the magnetic properties periodically in space. For example, the saturation magnetization or the relative permeability. And this ultimately allows for the band structure control of magnons. So think of Bragg scattering in a lattice. So here's one example where we have a one-dimensional magnonic crystal. It's made of nickel iron. So permalloy, PY is the abbreviation for this nickel iron alloy, cobalt nanostrips. So you can see them here. Here's the scale bar, it's 1 micron. And then there are spin waves launched at some end. And in this paper, they report the dispersion. So you can see here frequency versus wave factor. And because of this magnonic crystal, because of the Bragg reflection in the lattice, they observe well-defined band gaps in this lattice. So this is the bottom line here is, this is analogous to photonic crystals in photonics. The beauty here is we can control individual elements, for example, by external field routines or by spin torques. My goal for today is to convince you that we can consider an artificial spin ice, which are these arrays of nanomagnets, as a very promising platform to realize a reconfigurable two-dimensional magnonic crystal. So we can see this. Here we have a square lattice with these elongated elements. They have a size of a couple 300 nanometers, and a width of about 80 nanometers. So I consider them, since I'm coming from a magnonics perspective or spintronics perspective, I view them as a reconfigurable magnonic crystal. So I have to answer this question. So why is it called artificial spin ice? For those of you who are not familiar with the term, let me briefly explain why we're talking about artificial spin ice. We're all familiar with water ice, right? Where we have oxygen ions here shown in blue. They occupy the lattice sites in a diamond lattice, and they are hydrogen bonded by an intermediate proton or two intermediate protons, which you can see here in red. Now, the lowest energy configuration turns out to be when the two protons here are close to one oxygen ion, and the other protons are close to another oxygen ion. So this is the lowest energy state. Now, this is called a ice state with an ice rule, and we can now map this on a spin system. And this is shown here. We represent now the distances between the oxygen ions and the protons, where the protons close to one oxygen ion are illustrated by the tip of the arrow. You can illustrate this now by these arrows, as you can see here. And this is the same configuration that you would find in crystalline spin ice systems. And these are pyrochloride materials like dysprosium titanate or holmium titanate. And there is a lot of interesting research that you can do in those materials. It's fantastic. What we are interested in is artificial spin ice. And the reason is we can just create them however we want, right? We can define the lattice spacing, the geometry, have complete freedom how to create them using electron beam lithography. We can also control defects locally, for example, manipulating the lattice or how the lattice is distorted, and we can image individual spins because of this planar structure using optical techniques. So here's the simplest example. That's a square lattice. And I believe there is a question. Am I right?
No,
sorry,
there
sir.
isn't.
Okay.
Yeah. No.
All right. So here we have a square artificial spin-ice lattice, and I'm showing here all 16 possible configurations. And you see that, for example, the type 1 and type 2 state, they are characterized by a 2-in, 2-out rule. This is the lowest energy state. And then we have high energy states like the type 3 state, which is characterized by 3-in, 1-out, or 1-in, 3-out, or the type 4 state where all spins are pointing inwards or all spins are pointing outwards. So this is essentially something like a double monopole. This was actually discovered in 2006. This is where the name to artificial spin-ice was introduced by Peter Fisher's group. It was published in Nature. And there had been a lot of interest in the slow dynamics in these type of structures. And closely related to the term spin-ice and ice rule is the term frustration. So frustration is not what you might encounter when you work in the lab and something doesn't work out the way you expected when if you're experimentalist, or when you are debugging your code and you're something going on that you do not quite understand in the beginning. No, what I'm talking here about is geometrical frustration. What does it mean? Well, let's assume we have here this triangle lattice with these nanomagnets, as you can see in South Pole and North Pole. And frustration, geometric frustration now means this third spin here doesn't know how to align. You can think about it, and the conclusion is that the third spin can never simultaneously minimize its interactions with both the other spins. It can align like this. One is happy, one vertex is happy, one is frustrated, and the same goes for this orientation. So there is some geometric frustration in the system, which leads to a high degeneracy of states, and this makes these materials very, very interesting for various reasons. Now we are using typically, we're making devices typically with elongated elements like these, with a length smaller than 500 nanometers and a width smaller than 100 nanometers. And we choose the thickness so as to achieve a single domain state. So typically, the thickness is between 15 and 20 nanometers. We got excited about this topic when this paper came out. This was a micromagnetic simulations work, and what Kliger and co-workers did is they defined a square lattice in their computer code, and then they ran micromagnetic simulations, so they numerically solved the Landau-Lifshitz equation that I showed you earlier. And what they then did is they introduced monopole anti-monopole pairs. So these are these high energy states I was referring to earlier. For example, here it's a type 3 state. And these monopole anti-monopole pairs are connected via a string. And these strings are shown here in this brownish color. That's essentially a chain of flipped spins. And what they found in their code, in their simulations, is that dependent on the number of strings and dependent on the number of monopole anti-monopole pairs in the lattice, certain modes appear in the resonance spectra. And we thought, that's interesting, because now you can think of using this as microwave filters, where you can send spin waves along specific directions along certain strings. You could even think of flipping individual elements and create a pathway for spin waves in these lattices. So the first thing we did is we did a very simple experiment. We patterned a square lattice on a microwave antenna and performed ferromagnetic resonance. I'm going to talk about this in more detail in a moment. Here, I just want to show you just the highlight. So we see here this rich mode spectrum, a lot of different modes. And in this paper, we found indications that we can indeed find indications of certain spin-I states present in the system using a simple resonance experiment. Usually to find this state here, you need to do magnetic force microscopy imaging. It takes a long time. So this is rather quick and you can get a sense of what state you're in. Around the same time, there were other people working on similar topic. So this PRB and this advanced function materials were published around the same time. And since then, there have been a lot of papers, too many to list them all here. But I do want to mention here 3 recent review articles on the topic of nanomagnonics with artificial spin-Is, if you're interested to get an overview. So now let me jump into the results that I would like to present today. First, I'm going to show you a comparative study between ferromagnetic resonance and brilliant light scattering in a square lattice. So ferromagnetic resonance is pretty simple. You have something in a device, it's called a vector network analyzer. You send a microwave signal from one port into an antenna, you excite dynamics and measure basically the absorbed energy by measuring the transmitted signal. When you're in resonance, you excite the magnetization dynamics, and therefore you have a loss of the microwave signal, and you can do this as a function of field. Second technique here is polar light scattering. That is based on the inelastic scattering of light on spin waves, or the quasi-particle picture of photons on magnons. And there are 2 processes, Stokes and anti-Stokes process, which is the creation and the annihilation of spin waves. This process is energy and momentum conserving. So this means that the probed, that the scattered light carries information about the probed magnons. And we can now analyze this very tiny frequency shift using highly sensitive interferometer and get information about the magnons that are present in the system. So much about the background. Let me show you some of the experimental results. So we have here a coplanar waveguide. This is a microwave antenna with 2 ground lines and a signal line. We pattern our spin-Is directly on the top of the signal line using electron beam lithography and deposition of 20 nanometers using electron beam evaporation, followed by a lift-off process. And this results in hundreds of thousands of elements on the signal line, which we expect to behave like an infinitely extended lattice. I'm showing here a scanning electron microscopy image with the dimensions. So you see it's rather small and the alignment is pretty good. Now, how do we perform the measurement? We send now the microwave signal in and measure the transmission, detect this with a vector network analyzer, and we get 1 frequency trace, the signal as a function of the frequency, the absorption as a function of frequency. We can now do this for each field step, and what we get is a color-coded image, as you can see here. So we have here frequency versus field, and the color represents the S12 parameter for the expert. So that's the transmission parameter. If the stark contrast means we effectively excite dynamics in the system, so we have a strong absorption. And we can now see these very pronounced lines here, and this what I call W shape over here, and there are some fainter modes here and there. Now, let's think about this for a moment. In this case, I'm applying the external field, the biasing field, along the x-axis. This is illustrated by this green arrow. And I'm also showing here a schematic of the lattice. Now, these most intense lines come from elements which are patterned parallel to the external field. Why is that? Well, the magnetization lies in the direction of the elongated elements, which are parallel to the external field. That's the easy axis. And therefore, the microwave magnetic field, so the Ørsted field here in red, is perpendicular to the magnetization. So we have a maximum torque, and we can effectively excite the dynamics and detect them. So these lines are coming from the horizontal elements. Now, what about these elements which are patterned perpendicular to the external field direction? Well, in this case, if the field is strong enough, we can pull the magnetization from the easy axis, which is now in the y direction. We can pull the magnetization in the x direction for high magnetic fields. And in that case, we again have an angle of 90 degrees between the Ørsted field and the magnetization. So we get some torque. And this is what we see over here. However, as we, sorry, my Siri just went on. However, as we now reduce the external field and approach zero field, the magnetization gradually rotates from the hard axis into the easy axis, which is aligned in the y direction. And remember, this y direction is parallel to the Ørsted field, and this means there is zero torque, and this is the reason why we don't see much of a signal over here in the low field regime. So bottom line here is, this resonance spectra doesn't give us the full picture. It's rather the technique that we use, but not the underlying magnetization dynamics that we see here. And therefore, we wanted to use a complementary measurement technique. And we used a brilliant light scattering spectroscopy. And I want to show you that this is a very powerful tool to detect the dynamics here. So let's see, I want to prove my claim that this is really true what I just explained regarding the elements with respect to the external field. So we shine our laser lights, 532 nanometers, single mode continuous laser, on the same system, on the same artificial spinized system as we studied by ferromagnetic resonance. Now we use a micro focus system, which means we collect the light over a large cone angle. So this means we also detect higher order modes that we are not able to see in ferromagnetic resonance. And the key difference, and I want to stress that, is we do not apply now any microwave drive. See, there's no microwave signal applied. We just measure the thermally excited spectrum. And what we get is, again, frequency traces that we can record as a function of field. And then we get a color-coded image. Here, the dark color represents the BLS intensity, which is directly proportional to the number of magnons present in the system. And you can immediately see there are many more modes visible, and you see more pronounced this W shape I was referring to earlier. And this demonstrates we are not sensitive here. We are sensitive to all magnetization directions, irrespective of their orientation with respect to the driving torque term. So we can see the eigenmodes of the system here very clearly with using brilliant light scattering spectroscopy. Now there is a question.
Yeah, hi. I just wanted to ask, of course, BLS gives you much higher sensitivity and possibly resolution as well. But could you achieve some of this by doing an angle-resolved FMR?
As a matter of fact, we did some angular dependence, and that's in this APL paper. I don't have it in my presentation, but you always suffer from the fact that you have to deal with the orientation of the Ørsted field. You could, of course, start thinking of patterning different coplanar waveguides with respect to the lattice. That's possible, but you have to do many more measurements, and here you get the information at once.
All right, thank you. Thanks a lot.
So to confirm this further, we used micromagnetic modeling, and there is a package called MuMax 3. You can run this on your computer on this GPU accelerated. And what we do now is we define the same type of lattice, same dimensions. We use one vertex with periodic boundary conditions, and we now apply a sync pulse with a cutoff frequency of 50 gigahertz to the system, and that is shown here in orange. We apply it along the y direction, and then we record the average magnetization and the average magnetization components and the spatial distribution for a duration of 20 nanoseconds, as you can see here. I'm plotting here the MZ direction, so the magnetization in the Z direction. We can now zoom in and see that once we hit the system with a sync pulse, the oscillation starts. So this is shown in blue. And if we wait long enough, the sync pulse has decayed and we see steady oscillations. So this is done for one particular field. We can now take the Fourier transform and see the resonances of the system. So these are the eigenmodes of the system. And we get 3 distinct modes. We can also, just as a sanity check, back Fourier transform the sync pulse. We see the cutoff frequency of 50 gigahertz. So that's important that we don't have any drive here above 50 gigahertz to reduce a spurious signal. Now we can do this as a function of field, just like we did the experiments. And this is the results. And we observe here a very good agreement between the modeling and the experiments. I also want to mention that we found here, by doing this angular dependence I was just asked about, we found the observation of a mode splitting, where the oscillations reside in different parts of the lattice. If you are interested, I would like to refer you to this paper. So next, I'm gonna talk about a specific type of artificial spin ice, which is based on nanodisks arranged on a honeycomb lattice. The experimental configuration looks very similar to before. We now pattern our devices, our magnetic elements, again on the signal line. You see here a scanning electron microscopy image. So this is this honeycomb lattice, and it consists of these disks, and we call them nanodisks because of the dimensions that you see over here. Now, we got interested in this kind of structure because in disks at low magnetic fields, you get something called the formation of a vortex core. And these vortices can be driven in the sub-gigahertz frequency range, and they describe then a gyrotropic motion, which you can see in this animation here. So the idea was, well, we could combine in the low frequency regime this gyrotropic vortex motion, and if we saturate the disks, we could observe spin waves in the system. So let's see how this turned out. So we performed our measurements like before, and we only see 2 distinct modes here, A1 and A2. We didn't see any vortex motion, unfortunately, in the experiment. But we also performed micromagnetic modeling. And you see here, again, pretty good agreement between experiment on the left and modeling on the right. And we can also perform static magnetization mapping using the modeling, using MUMAX. So here you see we sweep the field from the saturated state in negative field direction to the saturated state in a positive direction. And I'm also showing here the color-coded image of the MX component spatially resolved. Yes, please.
So about this mode splitting, is it because you have a degree of freedom and you can have clockwise and anti-clockwise rotation of these, or what's the origin of this splitting?
The origin is just it couples, so you can get some modes which, if you rotate the angle, some of these just go back 1 second. Some of these modes, they go down, they become very, very flat, and eventually these modes here go up, and they merge and they cross. And it could be interpreted almost like a hybridization of the modes. And then there is because they are different types of the lattice, they are at the same frequency.
Okay, yeah, okay, got it. Thank you.
So that was really, really quick what we observed there. All right, so the beauty now about micromagnetic modeling is that we can do these simulations spatially resolved. So I'm showing here the statics. So this is the static magnetization configuration at -800 Ørsted. So this is this green dashed line. And I'm showing here 2 modes, the low frequency mode, A1, and the high frequency mode, A2. So this is the high frequency mode and the low frequency mode and the static magnetization. And what we observe here is that for the low frequency mode, the dynamics are located in the oblique elements, whereas the high frequency mode is located in the horizontal elements. Let's see how this behaves if we increase the field. So this is at -200 Ørsted. Here we see the onset of some curling in the elements, but still, although these are higher order modes, we see that still the low frequency mode is located in the oblique elements, and the high frequency mode is in the horizontal elements. Now, if we cross zero field, we indeed see the formation here, at least in the simulations, of a vortex core. So this is a flux closure state. And we also saw in the simulations this gyrotropic vortex motion at 257 megahertz. And this is just assumed in version of this gyrotropic motion. So after we saw these simulation results, we thought, that would be nice to see experimentally. And we have this technique, Brilliant light scattering spectroscopy. I talked about this earlier, but in that case, previously, we only focused the laser spot and we didn't do any spatially resolved measurements. But here, the elements are bigger, so we decided to do some 2D mapping. So we placed our sample here under a microscope objective lens. We have here a 2D scanning stage with an accuracy of about 20 nanometers, and we have a magnetic field. This light is focused onto the sample and then sent back to the Fabry-Perot interferometer, where we analyze the frequency shift. We have also a photodiode for adjusting of the focus and a CCD camera to see where we are on the sample, and we also use some pattern recognition. So let's first perform the same type of experiment as before. We do basically an FMR measurement with BLS, and we focus the laser on one spot, change the field and the resonance frequency, the excitation frequency, and we see those modes. In this case, the resolution is not very good. But nonetheless, we see here an agreement between BLS and the FMR measurements. The advantage here is we can do the space resolved measurements. And we did this. So let's just remember the low frequency mode was in the oblique elements. And we now perform our BLS measurements. So these are color-coded images where red means a strong spin dynamics signal. The scale bar here is 1 micron. And I'm showing here in gray superimposed one vertex of the lattice. And you can indeed see that most of the dynamics are already residing in these oblique elements. Now we can also take a look at the high frequency mode. And indeed, we see that the dynamics are mostly located in the horizontal elements. So the bottom line here is we can use this type of artificial spin ice for the observation of localized dynamics in those systems. So that's the first step. If you think back about the idea of using these strings to send information along these strings encoded in spin waves, so this is a first step showing that there are indeed localized dynamics in these lattices. There's a question?
I wanted to ask if for the BLS experiment, are you still using thermal magnons?
Oh, very good question. In this case, we do not. In this case, it's not a thermally excited system. We specifically populate the modes at 7.1 and 7.7 gigahertz. Thank you very much. Excellent question.
So do you have a chance of detecting thermal magnons?
I think we did not do it at that time. That was the first measurement we did in the BLS lab. I believe we did not take a look at this. This is an interesting question.
All right, thank you.
Yep. All right, so in the remaining time of my presentation, I want to introduce a new type of artificial spin. So this is a bicomponent array of nanomagnets, and we got really excited about these results. So first we did 2 control measurements. We fabricate as before using electron beam lithography, e-beam evaporation, and lift off our lattices. So first we have here control measurements, just only nickel iron, so permalloy. And I show this here in red color superimposed to the SEM image. And then we do a lattice with only cobalt iron, and I'm showing this here in blue color. And then we defined bicomponent arrays, here with nickel iron on the horizontal elements and cobalt iron on the vertical elements, and the complementary lattice with cobalt iron on the horizontal elements and nickel iron in the vertical elements. And again, I'm doing this just because of the relationship of the RF drive, so the Ørsted field, and the direction of the elements. And you can see from these SEM images that we got a really nice alignment of these elements. So this is a two-step electron beam lithography work. So Moshtaba spent a lot of time figuring out how to do the alignment to get this kind of precision. All right, so now we can do our measurements, and I want to jump just right into the results. So these are these FMR maps, and I'm showing here the all permalloy system. Red means permalloy, so nickel iron. Here's the all cobalt iron system, and you see these lines here are from the horizontal elements. The line is much broader because the Gilbert damping of cobalt iron is much broader. And you can also almost see here this W shape that would extend to higher fields, but in this probe station, we're not able to extend to such high magnetic fields. Now let's take a look at the bicomponent lattice. For the case when nickel iron is in the horizontal elements and cobalt iron in the vertical elements, and the complementary lattice with cobalt iron in the horizontal elements and permalloy in the vertical elements. And just by staring at those maps, we can immediately see the similarities and how they relate to each other. We now used a analytical formalism to fit our data. And again, this is real calculations. So we see here in the nickel iron elements, which are in horizontal direction, are shown here by these red dashed lines. The nickel iron vertical elements are shown by these dotted lines. Then I'm showing here the cobalt iron horizontal elements by these dashed lines, and the cobalt iron vertical elements shown by these blue dotted lines. So we get a pretty good idea about what is going in this system, but there are other modes which we are not able to calculate analytically, and for that we use micromagnetics. So let me show this to you here. Again, nickel iron horizontal elements, cobalt iron vertical elements. I'm applying a field angle of 0 degrees. We show here the experiment on the left and the simulations on the right. We get a pretty good agreement here. And the beauty about the simulations is we can easily identify the sublattice dynamics using the simulations and identify which lattice corresponds to which mode. So red is permalloy and blue is cobalt iron, and we can now know which modes correspond to what. I'm superimposing this here to the experiment. Now, this is not particularly useful for 0 degrees because we can use the analytical formalism, but it becomes unequally more challenging to analyze this if there is an in-plane field angle. I'm showing this here for 60 degrees, and you see here the modes become flatter. And there is a step-like feature here when the elements switch, and then there's a step-down feature in the resonance spectra. So where is this coming from? Now, let me advance the slide so we see this also in the simulation, step up, step down, and this coincides with the switching of the cobalt iron that you can see here very nicely in the simulations. We can now also do space resolved simulations. I'm showing here this mode. So we see that this mode is residing in the horizontal permalloy elements. And when the permalloy switches at this point here, this mode changes its tilt, as you can see here. And as we increase the field further, there is the step down line feature, and that's when the cobalt iron switches here. And remember, the cobalt iron is in the vertical elements, and it affects the dynamics in the horizontal elements. And we see now the formation of a higher order mode in the horizontal elements. We can also do this for the complementary lattice. So let's take a look. So we have here 75 degrees. This is cobalt iron. on the horizontal elements, there's a step down lighting feature and then step up feature. And you can also see here nicely that this step down feature here coincides with the switching of the permalloy, which is this faint line here. So again, I'm plotting here the horizontal elements. That's this mode before the switching occurs. So we see the tilt. Now let's increase the field up to the point when nickel iron switches. When the nickel iron switches, we see the formation of a higher order node. It's not as visible as in the other bicomponent lattice, but nonetheless, we see that. And then when the cobalt iron switches, well, we see the change in the tilt in the magnetization oscillations. So the bottom line, the key message here is the switching of the vertical elements can be seen in the dynamics of the horizontal elements. And by changing the materials on the lattice sides and modifying the in-plane field angles, the dynamic behavior can be tuned. And to show this tunability, I'm going to show this now, the switching field extracted from the experimental data as a function of the in-plane field angle. So I'm showing here 60 degrees. Red again is permalloy, blue is cobalt iron. I'm doing this now for all different in-plane field angles, and I get this map. I can also do this for the complementary lattice and analyze this, and I see it as these blue and red faint curves. We can also compare this to the simulations here. So the simulations are shown on the bottom, and we get a good agreement between the experiment and the simulations. And we see from the simulations that it's eventually possible to reverse which sublattice switches first. So this is in this position or that position. We do not quite reach this regime in the experiment, but in principle, it should be possible to determine which lattice switches first. So I only just want to mention very quickly, we have also done this for different types of lattices. We are still working on the analysis, but you can see here, for example, for the honeycomb lattice, it becomes even more complex to analyze this. And here are just some results where we also get a pretty nice contrast in the FMR spectra, and the work on the analysis is ongoing for those lattices. Now, before I wrap up, I want to briefly advertise studying physics and astronomy at UD. We offer a PhD program, and applicants with a bachelor's degree may directly apply to the PhD program. We have a lot of different core research areas. I am here representative of the condensed matter and materials physics. I'm also listing here some junior faculty. So all of these people, including myself, joined UD within the past 3 or 4 years, and they're all looking for graduate students. I also want to mention that graduate students are well supported by teaching research assistantships with 12 months stipends exceeding 28K per year, and a full tuition waiver. And we have this really nice clean room where we do our samples. I also have here a photo of our campus, which is located in Newark. It's very conveniently located between Baltimore and Philadelphia, and it's also not far to New York City, so very nicely located on the East Coast. And I'm sure that if any prospect students have questions, that Professor Khalid is willing to tell a little more about his experience at UD. So if you're interested, take a look at the website physics.udel.edu, and you can also find the information how to apply to our program. So with that, I want to conclude. I hope I could show you that Brilliant light scattering is a powerful technique to explore dynamics in magnonic crystals and artificial spin ice. We saw localized dynamics in this honeycomb nanodisk array by BLS, and we have here the potential to implement gyrotropic vortex crystals with magnonic crystals. And we were successful in fabricating these challenging bicomponent arrays where we saw emergent dynamics dependent on the sublattice magnetization switching of the different sublattice dynamics. I again want to acknowledged funding. We're very grateful for support by the US Department of Energy. I'm very happy to take any questions. You can also shoot me an email. My email address is over here. It was a real pleasure, and I'm happy to take any questions. Thank you very much.
Yeah, thank you, Ben, for such a nice talk and presenting such wonderful results with us. So, yeah, it's open for questions. So if anyone have questions, please raise the hand, the virtual hand that is, and we will let you talk. Yes. Sabi. Yes, Sabi. You can.
Thank you very much for such an excellent talk, Benjamin. I wanted to ask about the optical excitation of magnons. If you could do micro resolved BLS in your laboratory, do you even consider the optomagnonic effect in which you excite these magnons with a laser pulse? And what about the feasibility of Moog measurements?
We could potentially do Moog. We do not have Moog in my lab, but Professor Chow and Professor Dodi are on UD's campus. They have a time-resolved Moog, which would be suitable for what you're suggesting. So you could think of electrically driven dynamics and probe it by Moog, or you could do pump probe experiments where you shine an ultra-fast laser pulse and do Moog measurements. And the time resolution is, of course, superior to BLS. There was a second question I
the
missed.
Optical excitation of these magnons.
So in this case, in the thermal measurements, we just use the thermally activated magnons, which are present to room temperature. Everything is done at room temperature, right? So we just probe the magnons and create and annihilate them, essentially. And when we do the microwave measurements, well, we populate certain modes that we can then detect predominantly.
All right, thank you.
Yes, any other questions? So Ben, I have a question maybe. So what's the what's limiting the time resolution of this BLS method, for example? So
I would say it's actually the cards that we have. So I feel comfortable saying that we can have like 100 to 200 picosecond time resolution. The problem that we are facing right now, so today I didn't present any time resolved measurements, but we of course tried to do that. The problem that we're facing right now is you need to apply a pretty strong microwave signal. And you need to have pulse microwave excitation, right? It's like a time of flight measurement. And the problem we are facing is that those switches, these pin switches, have a switching time of a nanosecond or two. And if you use this as high power, they don't work reliably. Yeah. So therefore, that's the trade-off.
Okay. Yeah. So you'll be interested in like picosecond dynamics, but that's limiting the.
For that, I would go to time resolved Moog.
Okay. Yeah. Good.
If I have a follow-up question, can I ask? Yes. Benjamin, does any of your work go into the study of Magnon interactions with other magnons? Some of your artificial systems may have strong plasmonic effects as well. So do you consider Magnon-plasmon interactions, or is there an interest to do so?
There is some interest in do so. We have a different project where we are interested in that, especially in hybrid systems with topological insulators. In these structures in artificial spin ice, I have, to be honest, not thought about these kind of plasmonic magnonic interactions. But in general, in my group, we are very interested in Magnon interaction, so magnonic hybrid systems, and also in Magnon photon coupling, so microwave photon and Magnon coupling. So we're working intensely on that as well. So, and just to follow up on this, so I mentioned in this APL paper that we recently published, the first topic that I showed, the comparative measurements between BLS and FMR. When we did these angular dependent measurements and saw the mode splitting, we got really excited because we first thought that this is a Magnon interaction in hybridization. But to be honest, we could not really confirm it. So therefore we call it a mode splitting and not a hybridization.
But can you maybe generate pathways in which you can make them interact?
I can't tell right now.
Yeah. Any questions from students or? So it was a very clear talk, so it's a very, very nicely constructed. So thank you, Benjamin, for taking the time. Yeah. So anyone else?
Thank you very much.
Yeah. So yeah. So let's thank Ben. If there are no, yeah, Sabi, yes, you would like.
Yeah, just wanted to mention that I'm also trying to learn Magnonics. So we recently built an FMR system which uses phase sensitive detection. We've been trying to grow some permalloy nanostructured materials and do angle resolved FMR. Recently we also got this micro BLS system. So we're in the final stages of setting it up. It's slightly complicated, as you may know, the alignment, and we do have a very strong focus on MoK measurements. So generally we do these measurements, Faraday and Kerr effects at low temperatures, but now we're trying to look at some more interesting phenomena, Magnonics, with these newly emerging class of two-dimensional materials and possibly organic inorganic structures.
Very nice. That sounds very exciting. I didn't know that you have a BLS system. That's great. That's great.
Just recently got one.
Will you be able to do low temperature measurements as well by BLS?
I think so. Yeah, up till about 5 or 6 kelvins.
That's fantastic. That's great.
So probably I'll talk to you more about this in a subsequent email and seek
Yes, I think we should probably talk at some point. Yeah, it would be nice if you could send me an email.
I will.
Yeah. Okay. So yeah, so with this I would yeah. So let's I would thank Ben again for taking the time and preparing such a nice presentation, understandable to pretty much an understandable lecture to a variety of a wide audience. And yeah, so thank you, Ben, again, and let's close this session till next week. So yeah, goodbye.
Thank you for the opportunity.
Yeah, thank you. Bye.
Bye.
So bye everyone.